In this example, we're going to find the Maclaurin series for the function e to the 2x. Now you remember a Maclaurin series is the same thing as a Taylor series, but Maclaurin series are the ones that are specifically centered at 0. So you'll see here that they never told us where they want the series centered, is because we should know that it's 0 because they told us it's a Maclaurin series. If they had said find the Taylor series for e to the 2x, they would have also had to have provided us with some value of c where they want the series centered. All right, so what we want here is we want to write e to the 2x equal to some series. But the thing is, I'm not quite sure at the moment what we're going to put right here. That's the problem, is we have to write this guy, express this guy as a series. So let's see if we can figure out what we need to write here in the series. All right, so most of this hinges on us remembering what is a Taylor series. Now, a Taylor series in general is a sum from 0 to infinity, the nth derivative of the function evaluated at the center divided by n factorial times x minus the center to the nth power. But if the center is 0, this would be like x to the n, because it'd be x minus 0 to the n and the nth derivative of f of 0. So that's our definition of a Taylor series. So we basically have to do these things. Now, remember though, the n factorial is always going to be in every Taylor series or every Maclaurin series. The x minus c to the n is going to be in every Maclaurin series and every Taylor series. It's this guy up here that's going to change, because this is the only part that depends on the function. It doesn't matter what the function is. This will always be n factorial, and this will always be x minus c to the n. So the meat of this problem is trying to figure out a pattern for these numerator terms that are the coefficients of the x minus c to the nth power. So what we typically do is we actually find a few so that we can try to determine a pattern. So we'll need f prime, f double prime, and f triple prime. And if we still can't find a pattern, we'll need to do even more. But hopefully 4 terms will be sufficient. So our function was e to the 2x. That's who we're trying to find the Maclaurin series for. So his derivative is 2e to the 2x. That's the chain rule. The derivative of 2e to the 2x would be 4e to the 2x. The derivative of 4e to the 2x would be 8e to the 2x. I'm assuming that you guys are pretty comfortable taking derivatives of exponential functions. Now, that's not the actual term that I want, because I don't just want all these derivatives. I actually want them evaluated at the center. So in our case, 0. So we also need to plug 0 into all these things. E to the 0 is 1. 2 times e to the 0 is 2. 4 times e to the 0 is 4. And 8 times e to the 0 is 8. So we get these values 1, 2, 4, and 8. So now I'm starting to see what the terms look like. And what I want to try to do, and hopefully you can do this in your examples, is try to determine some pattern that these guys are going to follow. So I'm trying to find almost some sequence of terms here where the 1 is matches when n is 0, the 2 matches when n is 1, the 4 matches when n is 2, 8 matches when n is 3, because these are going to be in the first 4 terms of the summation that starts at 0. So let's think about this for a minute. Do you see any patterns for 1, 2, 4, 8? I think so. I think the next one would probably be 16, then 32, 64, 128. This looks like 2 to the n to me. And so when you're writing your pattern down for the numerator part, I think we would have 2 to the n. Let's try it. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. Yeah, I think that works. That's our numerator. The denominator is always n factorial, so that's quite simple. You never change that. In every example, you'll have an n factorial. And then most people, when they write the a sub n, most people do not include this x minus c to the n. They'll just write that at the end of this. What we just found was the pattern for the first 2 terms. And the great thing about this is, notice, does this right here, does that depend on f? Not at all. The original Taylor series definition had an f, but we're trying to write it not in terms of f and f's derivatives and whatnot. So we have 2 to the n over n factorial. So let me go back to my original page here. So this will be the sum from n equals 0 to infinity. And the pattern we found was 2 to the n over n factorial times x minus the center, which is 0 to the nth power. So we did it. We are done. What we just created here was a power series representation, actually Maclaurin series because it's centered at 0, but it's still a power series, or you can call it a Taylor series representation for the function e to the 2x. So you basically follow these steps no matter what your function is. You take a few derivatives, you plug in the center, you look for a pattern, and then you take that generic pattern and you stick it in this template here.